Good morning, it's the physics video lecture, physics 105B, video lecture 31. I'm going to recapitulate what we did last time with the linear stability analysis and really just work our way through that homework problem, leave you guys a little bit to do, and a little bit more of an application in the same theme. But so once again, linear stability analysis. This time we've seen it before, and so I can just bring out some of the more interesting points there, and then we'll apply it. So again, the idea is that we have a differential equation dx dt, x n component vector, is equal to a vector function of x. And this becomes really interesting when it's a nonlinear differential equation for which there doesn't exist some recipe for getting the answer. Okay, nonlinear problems are very difficult. So what we have in addition to this is a point x sub 0 such that f of x sub 0 vanishes. And looking towards our application with the spinning top, with the rigid body motion, we know that this constant vector, being an omega vector, actually represents a dynamical state of the system. It's rotating, but it's just, the rotational axis is pointing in one particular direction. So under these circumstances, we linearize the expression by just expanding f in a Taylor series. F of x0, which we know vanishes, plus then the first derivative terms, which I'm just going to call df of x0. That is a matrix, an n by n matrix times x minus x0, and then we can keep going, but we turn this into our new differential equation. Now let z be this small quantity x minus x0. Okay, so that's small, and then we have dz dt is equal to A, and I'll just say what that is, right? That's that matrix A times Z. So there's a linear differential equation with constant coefficients. And the general solution, write that here, sure. General solution would be z is equal to the sum of, in fact, here need a little more room. At this point, it's looking like our discussion of small oscillations. And for good reason, because the discussion of small oscillations was reduced to a linear differential equation, more or less of that form. So once again, the general solution, that's what I'm talking about. Z of t vector, it's a sum of coefficients sub k, a sub k, e to the lambda sub kt, k equals 1 to n. So these are just complex coefficients. Complex numbers. These here are the eigenvectors of A of the matrix A, which is defined right up there. And these lambdas are the eigenvalues to those eigenvectors. And then we see if we have a real part, you know, if the eigenvalues are pure imaginary, then the whole thing's just an oscillatory system. If there's a real part that is positive, then this thing will grow out of bounds, and that defines unstable, okay? If real part of lambda sub k is positive, then we have the instability. Then it's unstable because this thing grows exponentially out of bounds. If the real part is negative, then of course this term gets decays exponentially, goes to 0. And if the real part is purely imaginary, then it's just oscillating, it's not growing, so it's not growing out of bounds. Remember that z is a small quantity. Okay. So yeah, the linearization plays a similar role to in the theory of small oscillations. What we do in the theory of small oscillations, let me put that as a note here. In the theory of small oscillations, we have a system with a local minimum. We expand around the local minimum to quadratic terms, okay? And then the differential equation turns into a linear differential equation, which is why we get something similar to this in the system of small oscillations, okay? So small oscillations means that excursion from equilibrium is small, and same here, except here we don't know if it's an equilibrium or not, okay? Because we don't have that potential well to begin with. Instead, we just have the dynamical equations, and we're analyzing them. So yeah, real part of lambda is greater than 0. Then we have the instability. So the note is, in the theory of small oscillations that we've studied, right, we did small oscillations for systems with many degrees of freedom. Expansion to the second order, about local minimum yields first order differential equations. First order differential equations. Oh, I'm sorry, not first order. We have a second order differential equation yields a linear differential equation. And at the moment, that's the relation we have there. I'll go into this first and second order difference in a moment as well. Okay. But first, let's go ahead and apply this now to our rotating system. I didn't bring the book to class again this time, but you know, I wrapped string around the book and showed you the tumbling nature. That was that instability we were talking about. So I hope you guys gave that a try. Okay. That's a demo you can do yourself, and you can make it a challenge too. Can you make it not tumble if it's rotating about the intermediate axis? You know, that would be a challenge. Maybe you could turn that into a bet, like a little carnival situation. Okay. But I didn't say that. Okay, so now let's go ahead and look at our system. Instead of x's, we have omegas. So I'll just write down our equation here. So we have d omega 1 dt I2 minus I3 over I1, omega 2, omega 3, and cyclic. I write them all down. Yeah, I will. D omega 2 dt. We're going to want to simplify this, of course. I3 minus I1 over I2. Omega 3 omega 1. 3 Well, we're going to simplify this for d omega 1 dt is equal to a omega 2 omega 3 d omega 3 omega 1 and c. Okay, so the definitions are there. C omega 1 omega 2. So this is our d omega dt is equal to f of omega. Okay, this is what I had instead of x. I've got the omega, and right, you can say it's equal to f of omega 1, omega 2, omega 3. That's what we need. Okay, so you can see we have that form, and we can also see it's highly nonlinear. So what we're going to do is, see, we can cycle through different values of A, B, and C in order to just test a single axis. So we'll go ahead and consider rotation about the third axis. Rotation about x3. That is to say, omega is going to equal 0, 0, omega, like that. That's our vector. So that's around the third axis. So what we need is that matrix. And that matrix has to be evaluated about this axis. Should we give this a, in honor of this being constant, we'll just call this an omega 0. Okay, just to be clear about that. So there's our dynamical system of equations. A, B, and C are a lot simpler than that, but they translate. Okay, so what is this d f of omega 0? That's what we could call it. That's d f I d omega j evaluated about this omega 0. So it's a 3 by 3 matrix. Let's just draw a big one here. See if we can fill it in. So df1, d omega 1, there's a 0. By the way, this matrix is going to have a lot of zeros in it. Nothing wrong. So df1, d omega 2 is a omega 3, and df1, d omega 3 is a omega 2. And we go to f2, that's this one. So df2 d omega 1 is b omega 3. df2 d omega 2 is 0. df2 d omega 3 is b omega 1. And then for the third one, df3 d omega 1 is c omega 2. df3 d omega 2 is c omega 1. And finally, we get a 0 there. We're not done though. Okay. Those are just those first derivatives, but we're supposed to evaluate these at omega equals 0, 0, omega 0. So I think I'll do that right here with a different color. Okay, I'll do that with a different color. So omega 1s and omega 2s are all 0. Okay. So we can strike that, we can strike that, we can strike that, we can strike that. Okay, those are all going to be zeros, and these are going to turn into, this is going to turn into, so these we retain, This will turn into A omega 0, this will turn into A omega 0, because that's what I called it. Okay. But you guys do that. So now you have this 3x3 matrix, but it's not that bad. So I think this is where I'll leave you guys in terms of the homework. Making sure, so that was 2 minus 3 over 1, 3 minus 1 over 2, 1 minus 2 over 3, okay, that's all fine. ABC. So now what you're trying to do is find the eigenvalues of this matrix. So the homework find the eigenvalues of the matrix. Okay, that's easily done. You know, you've got lambda times the unit matrix minus A. The determinant of that is equal to 0, and A is, of course, this matrix we have right here. So you get those eigenvalues, and since we chose one axis, the x3 axis, so you have to go through the different combinations of moments of inertia, show that if, in this case, since this is around the free axis, if I3 is the intermediate moment, then we get instability. Which is to say, if I3 is the intermediate moment of inertia, then the real part of the eigenvalue is going to be greater than 0. And yeah, you just cycle through the different combinations of these things. And you know, you translate back, you've got your A and your B, so yeah. It's practically staring us in the face, but you guys go ahead and do that. It's a pretty satisfying problem. Then you can make sure you understood everything that we've done here. Okay, so that is a good exercise that we've pretty much done together. And it's good to go through it though, because there are a lot of places you can make errors. For example, if you're just left with this matrix and forgot that you had to evaluate it here, then you know you'd have this complicated matrix. But it's actually a lot simpler. It literally only has these two non-zero contributions. Okay, that'll give you no problem. Okay, so I'm going to go back to the differential equations and the linearization. And you know, you'll remember our harmonic oscillator, the way we tackled it originally, and in fact our small oscillations theory this semester, it's the expansion of a general potential well, or expansion around a local minimum. And like I just said a few minutes ago, that is a linearization. So let's look at the damped harmonic oscillator. So let's call this example of a linearized equation, because that's what it is. A linearized equation, and it's our damped oscillator, so we'll go straight to x second derivative plus 2 gamma plus omega naught squared x equals 0, right? We've studied that thing a lot. So we have omega naught squared is equal to k divided by m, and 2 gamma was b divided by m for whatever it's worth, right? That was the friction term. but that's just for completeness here. Now this is a linear differential equation, second order, but you guys have probably studied how it's possible to turn these into first order differential equations. So now let x1 be x and x2 be equal to x1 dot, which is equal to x dot. So instead of one differential equation of second order, we're going to have two first order differential equations, and they can be expressed in matrix form. So this equation reduces to d dt vector x1, x2, and now we're going to have a matrix x1, x2. So first of all, okay, let's just do this. So dx1 dt is equal to x2. So in terms of this matrix, we have a 0 and a 1, okay? Dx1 dot is equal to x2. So that's what the first row of this matrix is. Now the second row, we have, because of this 2 gamma x dot, our x2 is going to be multiplied by a 2 gamma, be minus, and so x2 dot, so let's go ahead and write this out. No, x2 dot is equal to x double dot. Okay, that's what that means. And that's minus 2 gamma x dot minus omega naught squared x. So we got a minus omega naught squared minus 2 gamma x2 minus omega naught squared x1. That's the idea. Okay. So minus omega naught squared x1, okay, row not column, minus 2 gamma x2. So this is the same situation we were just talking about with our other system. Okay, we have two components instead of 3. And I'll put this on a homework as well because this is really interesting. What you want to do is find the eigenvalues, except I'm tempted to do it right now. The eigenvalues. You know what? I'm going to do it right now, and you guys will write it up as well, just to, for good measure. Find the eigenvalues of the matrix. You could find eigenvalues and the eigenvectors, and eventually you'd come up with just the solution to this that we've studied before. So let's just do the eigenvalues. That's worth it. Go ahead and erase this. So again, we're looking for precisely this. Lambda times 1 minus A. So in this case, since that's our matrix A, we would have the determinant of lambda minus 1 omega naught squared lambda plus 2 gamma. Okay, because we took the minus negative of that matrix. Okay, and what's that determinant? That's lambda squared plus 2 gamma lambda plus minus this omega naught squared equals 0. Of course, we've seen this before. So we have lambda equals 1/2 negative b, so negative 2 gamma plus minus the square root of 4 gamma squared minus 4 omega naught squared. And we'll simplify that. Lambda equals, in fact, you know what we'll do? Underdamped, of course, we don't want to. So the so-called underdamped case, which means that we can flip these and pull out I, so we have minus gamma plus minus I root omega naught squared minus gamma squared. Okay, now since this was the linearization of a physical system, okay, that's how we get these small oscillations in the first place, right? So that's a linearization. Then what we just did was a linear stability analysis, and we say, okay, now this is purely imaginary, and we're needing gamma to be positive. Okay. See, if gamma is positive, then the real part of lambda is negative, and then we have stability, and in fact, a damped oscillation is stable. On the other hand, if we just didn't know what these things mean, then we could require that in order for the system to be stable, gamma has to be positive. And if gamma were negative, then it would be unstable, it would be anti-stable, right? So yeah, this example is well worth pondering because we know it so well, and this is how it fits into the formalism. Okay, so I'll put a couple of words there. I was going to have you turn that in, but you know, if I make it thorough enough, you turn it in your notes thoroughly, and then I can assume you understand it. Okay, so I'll just use this to. Imagine we're mathematicians and they just gave us this differential equation. We don't know what it means. Okay, so then we would actually come to characterize these parameters. So let's see, let's fill in a couple words here. So what we're studying here, this is what we know as the underdamped case. So that just means that omega naught squared is greater than gamma squared. So that restricts those parameters a bit. But it doesn't tell us if gamma is positive or negative. And so what we see that negative gamma less than 0 stable system. Okay. And therefore gamma is positive. Okay. So the damping coefficient as we built it in has to be positive. Now here's the thing, in terms of this system or say a more exotic system, suppose this gamma here depends on various other parameters. Okay? So if this gamma were to be a function of some other parameters, there could be a regime in which gamma changes sign from positive to negative. And then we'd say, you know, there's a regime in which the system goes from stable to unstable. Okay? I'll put that as a note as well. If gamma depends on parameters such that it can change sign, right? It can change from positive to negative, then those parameters, whatever they are, those some kind of physical inputs would control the stability of the system. Then those parameters control the stability of the system. So this is actually really far-reaching. In fluid mechanics, a system of linear stability is hugely developed and still not completely solved. Okay, and it actually goes back to a linearization, not of a simple, 2x2 dynamical system, but of a more complicated system. But actually, the exponential trial solution is common to both of them. So in terms of eigenvalues, that's actually what would be going on. Okay, so I think I'm going to leave it at that. We have another interesting topic coming up. Yeah, I'll leave it at this for this time. The next topic is going to be motion in an accelerated system. We can start talking about things like Coriolis forces and the Foucault pendulum. That's going to be our big goal for next time. But for now, we'll leave it at this and see you next time.